right, welcome everybody. So today we're going to talk about Ka, Kb, and Kw, how they're used mathematically, and what the difference is between them. So by the end of this video, you guys should understand how hydronium and hydroxide ion concentrations are calculated, both for strong acids and bases and for weak acids and bases. So first we're going to start off with definitions. There are a couple of different scientifically accepted definitions of acids and bases. So the first is the Arrhenius definition, and that's the oldest definition. So Arrhenius defined acids as anything that will dissociate, aka dissolve in water, to produce hydrogen ions. So an Arrhenius equation would have the acid, and then it would be splitting up into its respective ions, one of which would always have to be hydrogen. Okay. Bronsted and Lowry decided to define acids and bases a different way, and they based their definitions around protons. So anything that donates a proton, which by the way is an H+, because a hydrogen atom without an electron is just a proton. So anything that donates a hydrogen in water is going to be an acid. And so what we mean by that is in water, what will happen is the acid will lose the hydrogen, so that simply becomes a minus on the other side. It donates it to the other species in the equation, in this case water, to produce H3O+, which is known as hydronium. Bases are also defined using two different definitions. So we have the Arrhenius definition, which tells us that anything that dissociates to produce hydroxide ions in water is a base. And so an Arrhenius equation would show my base splitting up into its ions, my cation, and then at least one hydroxide. Bronsted and Lowry again formed their definition around the idea of the proton. So anything that accepts a proton in water is going to be a base. And so if I had a reaction between a base and water, the base would take a proton away from water to become BH+, and then what's left of water would be the hydroxide ion. Now, strong acids and bases are substances that will dissociate nearly 100%. They are nearly all products. In fact, we assume that they dissociate 100%. So for strong acids, the hydrogen concentration is going to be equal to the concentration of the acid. So my hydronium concentration, my H3O+ concentration is equal to whatever the concentration of the acid is. For bases, the concentration of hydroxide is equal to the concentration of the base, unless the strong base has multiple hydroxide groups, in which case I would take the number of hydroxides in the chemical formula and multiply it by the concentration of base to get my concentration of hydroxide in the solution. So let's say that it was something like CaOH in parentheses with a 2, then I would take the molarity of the calcium hydroxide and multiply it by 2 because there's 2 hydroxides dissociating. There are several strong acids. So we have hydrochloric, hydrobromic, and hydroiodoic. Then we have a lot of oxyacids, so acids containing polyatomic ions. So HClO4, that's perchloric acid. We have H2SO4, sulfuric acid, and we have HNO3, nitric acid. Bases are going to be anything that contains an alkali metal and hydroxide. In addition to that, there's a few from the alkaline earth metal family: calcium hydroxide, strontium hydroxide, and barium hydroxide are going to be your strong bases. So calculating the hydroxide ion concentration and hydronium ion concentration for strong acids and bases is pretty easy. You just kind of have to look at the molarity. But we have to be able to do this a different way for weak acids and bases. And so we use Ka for acids. Ka is known as the acid dissociation constant. So if my equation looks like this, if I have my acid in water, and again the acid donates the proton to become the anion, and then I have hydronium, then looking at this equation, the way that I would write my acid dissociation constant expression would be my products, Again, it's just like equilibrium. It's always products over reactants. So it would be the ions, my two products, over my reactant. Now, I'm only going to use HA. We're going to leave out water. So in the acid dissociation and base dissociation constant expressions, we leave water out of those particular mathematical calculations. It is necessary to use Ka to calculate the hydronium ion concentration for weak acids. And that's because weak acids have very, very small equilibrium acid dissociation constant values. They dissociate very little. So we can't assume that the molarity of the acid is equal to the molarity of the hydronium ion. They're going to be very different, okay? Because very few of those reactants are actually going to form products. Very few of these molecules of acid for a weak acid are actually going to become ions. So for weak acids and bases, since HA, the concentration of acid, is not equal to my hydronium ion concentration, we have to use Ka to do some of these calculations. So here's an example. I need to calculate the hydronium concentration of a 0.1 molar solution of hypochlorous acid. So I have a Ka value given here. First, though, I'm going to write the dissociation equation for this acid. So HOCl in water will donate a proton to water, so I'll have OCl minus and hydronium. Basing my equilibrium, my acid dissociation constant expression on this equation, it's going to be my products, so Ka is equal to my products, OCl minus and H3O plus, over the concentration of my acid, and I'm going to leave out water. Now we can plug in known values to this expression and solve for X. And what happens is, for every one of these acid molecules that dissociates, I get one OCl and I get one H3O plus. And so, since I know that I'm moving in this direction, think about equilibrium, every time this dissolves, I get X here and I get X here. And so really, I'm going to put X in each one of these blanks here on the top of this expression. Since I don't know those concentrations, I'm going to plug X in there. So really what I end up with is X squared on top. Now I'm going to set that equal to the Ka value that they gave me, which was 3.5 times 10 to the negative 8th. Now here's the deal. A lot of times, since these dissociation values are so small, we can actually neglect X in the denominator. So that actually makes the math a lot easier. We're not going to have to use any quadratic functions here. You can tell whether or not to neglect X in the denominator if you multiply K by 100. If you multiply K by 100, and the concentration of your acid is still way, way bigger than K, then X can be neglected, which means it can be removed from the denominator. So we knew that we were moving in the forward direction, so we should be losing from our concentration of acid. But honestly, because this dissociates so little, we're losing so little from the reactant side that we actually don't have to subtract at all. We can just put the concentration of the acid there. We don't have to put 0.100 minus X, we can just put 0.100 because that was the molarity of the acid of the HOCl in this problem. And so you would simply do algebra and then solve for X. X, remember, represents both the concentration of our anion and our hydronium ion concentration. So once we solve for X, that is the concentration of H3O plus. Okay. For bases, this works exactly the same way. Kb is the base dissociation constant. And so if my base goes into water, it's going to accept the proton to become BH+, and then hydroxide is the other product. And so my base dissociation equation would have my two products on top, and it would have the concentration of the base on the bottom. Again, we would leave out water from these expressions. Again, because weak bases tend to dissociate very, very little, we can't assume that the concentration of the base is equal to our hydroxide ion concentration. So it's necessary to calculate Kb. Use Kb in calculations for weak bases, okay? So another example problem that we have here, calculate the hydroxide ion concentration of a 0.0015 molar ammonia solution. Again, I would have my NH3 in water becoming NH4 and hydroxide. And so my Kb expression would be my products over reactants neglecting water, taking that out of there. And if I substitute values into this equation, I can actually drop 1.8 times 10 to the negative fifth in for Kb because that value is given to me. I can put the concentration of the ammonia here. And I don't know the concentrations of these products, but I do know that they'll be equal to each other because in this equation there's a 1-to-1 mole ratio. And so for every ammonia that dissociates, I'm going to get one NH4 ion and one hydroxide ion. And so this will be x squared on top. And so what you end up with is x squared over 0.0015 equals 1.8 times 10 to the negative fifth. And since that x represents the concentration of NH4, and it's also going to be the same as the concentration of OH minus, once I find x, that would be the answer to that question. So a lot of times you'll see complicated problems, or they seem complicated, where they give you a mixture of several acids. So honestly, only the acid with the greatest acid dissociation constant will affect your hydronium ion concentration. So your calculations for hydronium are just going to be based on that acid. So don't even look at the other ones. If you have a mixture of acids, then you would only look at the one with the greatest Ka value, do the calculation for that one, and that would be your H3O concentration. Why? Because the other ones probably dissociate so little that their values don't even matter in the end. So for example, if I had this problem right here, calculate the hydronium ion concentration of 500 milliliters of 5 molar nitrous acid, which has a Ka of 4 times 10 to the negative fourth, and 500 milliliters of 1 molar cyanic acid. Now this one, I think it's like 6.2 times 10 to the negative 16th, I think is what that number is supposed to be. That is a much lower value than the Ka value for HNO2. And so I'm pretty much just going to ignore that guy right here. Now this actually, we can't just use 5 as the concentration of this acid, because what we're doing is we're diluting it. If I'm taking 500 milliliters of the acid and putting 500 milliliters of something else in it, I am changing the concentration. So I'm going to write my equation just for this acid, because that's the only one that matters. Then I am going to write my acid dissociation equation. And then we're going to plug numbers in. But this number, because I diluted the solution, is not going to be 5. To find the concentration of HNO2, I would have to use the M1V1 equals M2V2 equation to find the new molarity of it. And I believe it would end up being 2.5 molar, I think, because we're doubling the volume, so we should be decreasing the concentration by half. So really what we would put in the brackets there would be 2.5. But just to make sure, you could find the new molarity using the dilution equation. Kw is the equilibrium constant for water. And it's really important as well. Water dissociates itself, which seems crazy. If I have 2 waters, what will happen is one will donate a proton to the other. So I'll end up with a hydroxide because one of the waters lost a proton, and I'll end up with a hydronium because the other one gained it. At 25 degrees Celsius, Kw is a known value. It's 1.0 times 10 to the negative 14th. Now that's at 25 degrees Celsius, but the dissociation of water itself is an endothermic process. And what that means is we can shift equilibrium by changing the temperature. So if heat is a reactant and I add heat, if I increase the temperature, then I'm going to move that towards the product side. So if I increase the temperature, the dissociation of water increases, which means Kw increases. So be aware of that. Kw is a function. It is the product of the hydroxide ion concentration and the hydronium ion concentration. It is also going to be the product of Ka and Kb. So Kw is equal to Ka times Kb. So for problems like this example problem here, if I'm given the Ka for the ammonium ion, and what they gave me was Kb for the base, right, the ammonia base, what I can do is if Kw is equal to Ka times Kb, and I need to solve for Ka, I can divide by Kb. So if I took 1 times 10 to the negative 14th and divided it by the Kb that I was given for this substance, well, actually so this is the base and this is its conjugate acid. And so if I have the value for Kb of the base, I can find the value of Ka for the conjugate acid by dividing. And that would give me Ka.